Arsenic and the Environment, presented by Cecilia Askins for American Public University. This presentation will cover the properties and abundance of arsenic in the natural environment, as well as the historic and current uses of arsenic. There will also be a review of some of the environmental guidelines related to arsenic, as well as the environmental impacts of arsenic from industry and the typical pathways to humans, plants, and animals. Last, we will review a case study related to the microbial transformation of arsenic in municipal landfill leachate. Arsenic has an atomic number of 33, with 33 electrons, 33 protons, and 5 valence electrons. Arsenic is crystalline metalloid found in the Earth's crust and is found in the environment in rocks, soil, water, air, and in biota. Natural concentrations of arsenic in soil typically range from 0.1 to 40 milligrams per kilogram. The element is typically found in minerals such as arsenopyrite, realgar, and orpiment. An iron arsenic sulfide, also called mispickel, is the most common mineral from which arsenic is obtained. Arsenic occurs naturally in the environment in both organic, arsenic atoms bonded with carbon, and inorganic, non-carbon forms. Inorganic arsenic, the most abundant type, occurs with many other elements, particularly sulfur, oxygen, and chlorine. Inorganic arsenic is the type associated with more adverse health effects for humans. The Earth's crust contains approximately 1.8 parts per million arsenic. The open ocean contains anywhere from 0.5 to 3 parts per million, and the solar system contains approximately 12 parts per billion. Historically, in Roman times and in the Victorian era, arsenic was considered the king of poisons, or poison of kings, and there are numerous accounts of both commoners and royalty using the odorless and tasteless poison for personal gains. A British physician named Thomas Fowler presented his arsenic-based cure-all tonic known as Fowler's Solution in 1786. It was used to treat skin conditions including psoriasis. It became apparent that people who used the arsenic-laden Fowler solution had significantly higher risks of developing cancer, particularly on the exact spot the solution was applied. It was phased out between the 1930s and 1950s. Arsenic was also used in pesticides, pigments, chemical weapons, and added to animal feed. In 1910, German pharmacologist Paul Ehrlich developed the arsenic-based drug Salvarsan, also known as arsphenamine, as a treatment for syphilis. This drug was incredibly effective and remained the top medicine for curing syphilis until penicillin became available in the 1940s. Ehrlich's development of Salvarsan was the first step toward targeted chemotherapy. Today, arsenic trioxide is a very effective drug used to treat people with acute promyelocytic leukemia. The current use of arsenic also includes metallurgic applications and some wood preservations, although some sources state that use as a wood preservative is diminishing. The environmental guidelines for arsenic have come about recently as a result of recognizing it as a potential toxin in its various inorganic forms. For instance, arsenic was listed as a hazardous air pollutant by the EPA in 1992. The EPA also has inorganic arsenic listed as a Group A carcinogenic hazard. Although the maximum contaminant level goal for arsenic set by the EPA is 0, the MCL, or maximum contaminant level for drinking water, set by the EPA in 2001 is 10 parts per billion. Worldwide, groundwater contamination of arsenic is widespread, and there are a number of regions where arsenic contamination of drinking water is significant. It is now recognized that at least 140 million people in 50 countries have been drinking water containing arsenic at levels above the World Health Organization provisional guidelines value of 10 micrograms per liter. The Canadian guideline for arsenic in water to protect freshwater aquatic life is 5 micrograms per liter. The sediment quality guideline is 6 micrograms per liter. In the 1990s, it was recognized that well water in Bangladesh had high levels of arsenic. In a highly affected area of Bangladesh, 21.4% of all deaths in the area were attributed to arsenic levels above 10 micrograms per liter in drinking water, although some areas had higher than 50 micrograms per liter, which is their national standard. It has been noted by the National Research Council that approximately 1 in 100 cancer deaths may be expected from lifetime exposure to drinking water containing 50 micrograms per liter or more. Arsenic has been identified in the natural environment in greater than 200 minerals. It occurs in both organic and inorganic forms, but is found to be more toxic in the inorganic forms. Also, the release of arsenic from minerals has been found to be enhanced by microbial action, discussed further in the case study. Arsenic exists in the environment due to anthropogenic causes related to industrial and domestic wastewater, as well as runoff and leachate from various sources and atmospheric fallout. Human pathways of arsenic include ingestion, inhalation, and absorption through skin and mucous membranes. Plant uptake arsenic through roots and foliage, and fish through their gills and their gut. Human health impacts from exposure to arsenic can include skin lesions, hyperpigmentation, keratosis, peripheral vascular disease, Blackfoot disease, and it is also a carcinogen. It has been found to cause cancer of the lungs, colon, urinary system, and liver, typically associated with occupational exposure. Although arsenic has a high acute toxicity to aquatic life, birds, and terrestrial animals, it appears to be an essential ultra-trace nutrient for chickens, pigs, and red algae, as deficiencies have been found to inhibit growth. Other forms of algae show inhibited growth and productivity from exposure to arsenic at concentrations less than 5 micrograms per liter. The chronic toxicity for arsenic is higher for aquatic life, but lower for land animals and birds. In the last portion of this review of arsenic in the environment, a case study related to landfill leachate containing arsenic will be examined. This study is important as worldwide approximately 37% of waste is disposed of in landfills, with only 8% being disposed of in sanitary landfills and 33% in open dumps exposed to rainwater. Speciation of arsenic governs toxicity and mobility and can undergo oxidation, reduction, and methylation from microbial transformation caused by various bacteria species. This increases its mobility and availability in the environment. This study was conducted at a municipal landfill in a metropolitan area of Sydney, Australia. The objective of the study is to examine the microbial transformation of arsenic in the landfill system within the landfill leachate. The study was conducted over a 43-day period where leachate was collected at a pipe that discharges to a leachate pond. The sample contained approximately 80 micrograms per liter of dissolved arsenic. The arsenic was present in various organic and inorganic species, as well as high concentrations of organic carbon and bacterial biomass, specifically bacillus. The presence of ferrous iron and sulfide in the sample also indicated that it had a strong reducing capacity. Arsenic spiking was performed in a nitrogen glove box in order to maintain an anaerobic environment, and the role of bacteria transformation was analyzed. Results indicated that bacteria present in the landfill environment plays a crucial role in the transformation of arsenic species. A data gap that was found is that there is little knowledge regarding the ecotoxicological effects of various arsenic species transformation to thiol organoarsenic species, which occurs due to interaction between the various arsenic species and hydrogen sulfide generated by bacteria in municipal landfill leachate. This microbially transformed and toxic thiol organoarsenic has the potential to penetrate groundwater and potentially increase availability and harm to human health. In conclusion, it is clear that arsenic, although it has a long history of either harming or healing humans, in some capacity needs further study, especially in relation to the various uses in the industrial sector and its subsequent release into the natural environments, with implications of harm to human health and natural ecosystems. The remaining slides are the references used to create this presentation. Thank you for your time.